In this video, we'll be discussing how to analyze and replicate the Latin squares design. So first of all, how we incorporate Latin squares into the statistical analysis component is very similar to how we incorporated it into the randomized complete block design. In the statistical analysis, now we're going to be including a second variable to account for the second blocking effect. So remember last time we had two variables, we had our treatment and our blocking effect. This time we're going to have three variables. We're still going to have the treatment, we'll be using tau for the treatment, but now we'll have two blocking factors, A and B, or alpha and beta, for those two blocking factors. Recall, typically when we use the Greek letter, we mean the fixed effects. When we use the Latin letter, we mean the random effects. Also, I'll mention this is the treatment effects model as opposed to the cell means model. So be aware of that as you're looking through this. Again, in this current design, we don't have any replications. That would be, recommended, or that would be incorporated through a second subscript here, or a fourth subscript here going on top of each of these, indicating the replications. But in this current design, we don't have any replications. Also note that none of these variables are multiplied together. We don't have any interactions. Epsilon is still distributed how we expect epsilon to be distributed in any statistical model. And we have I, J, and K. Now note what's different here. All of these are going out to the same maximum numbers of factor levels. So this is very different than what we had in the randomized complete block design, where the treatment did not have to have the same number of levels as the blocking factor. But in our Latin squares design, remember we said we need to have the same number of rows, the same number of columns, and then our treatment effects, in this case that's going to be J, whatever the subscript of tau is. So in this case that's going to be J. Our treatment effects are going to have the same number of treatment effects as we do blocking levels. So again, tau is the treatment effect, alpha and beta are rows and columns, and the statistical analysis is going to be just like the ANOVA. It is an ANOVA. This is an ANOVA with three factors now instead of with two factors. So expect to see a lot of what we've seen previously. Now in this case, we're going to have the sums of squares totals, the sums of squares rows, the sums of squares columns, the sums of squares treatment, the sums of squares error. Now these are found in the regular way. So think about what you had before, where we had the sum of squares for the rows being the double sum. Now it's going to be the triple sum over all the rows, columns, and treatments of y sub I dot dot bar minus y sub dot 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 bar quantity squared. This is going to be the exact same thing. I think our columns was not J but K, so the triple sum of y dot dot K bar minus y dot 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 bar quantity squared, and then the treatment is going to be the triple sum of y dot J dot bar minus y dot dot bar quantity squared. And then of course our total is that triple sum of y sub I j k minus y dot 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 bar quantity squared, and then we find the error from subtracting. So this is all exactly what we would expect from previously. So don't get too confused here. Just go back to what we had previously, and now that we're adding that third variable in, you're going to add a third sum that you're summing over, and you're just going to calculate that third variable exactly how you'd expect to. For the sums of squares for the rows, columns, and treatment, again, remember this is going to be the same. Now, if we had traditional three-factor ANOVA, they wouldn't all be p minus 1, but because here we have all the same factor levels and all of the blocking factors, and in the treatment factor, they all have p minus 1 degrees of freedom. The total number of degrees of freedom is p squared minus 1. That's the number of replications. Now, the error degrees of freedom is the difference. In this case, the error degrees of freedom is going to be a little bit different than what we'd normally see, but in this case, the error degrees of freedom is going to be p minus 2 times p minus 1. This is changed from the randomized complete block design, where we have p minus 1 times p minus 1. So here we have our ANOVA table. So in our ANOVA table, again, we've got the sums of squares that we're calculating in the similar ways before. We've got our degrees of freedom. We've got the mean squares. And then remember the interesting piece here, we do not incorporate the F statistic for any of our blocking factors. So if we have rows and columns as the blocking factors, that was the setup that we did in the last video, then we're not going to have the F statistic calculated for any of those blocking factors. All that we're looking at is the F statistic for the treatment. That's all we care about because, again, by definition, blocking factors are factors that we do not care about. If there are factors we care about, we shouldn't be using them as blocking factors. Now, all of the same assumptions and assumption checks are incorporated in this Latin squares design as with the randomized complete block design. So independence, normality, homogeneity, variance, all of this has to be checked in the exact same way. We still have that same error term. The error term distribution hasn't changed. So you're going to be using a lot of the same tricks that we showed in the last video to be checking each of these different pieces, except now you of course have another blocking factor to consider. But in terms of the error checks, the way that we've set those up in that previous video with the randomized complete block design, it's not going to change even if you have a third blocking factor saved, that you can do a third box plot over that blocking factor. Now this is important. We are still assuming the additive model. That is, we're still assuming no interaction. What this practically means is that we still assume that the relationship between the independent variable is only with the dependent variable, that the relationship between the independent variable and dependent variable doesn't depend on what level of the blocking factor we're at or what combination of the two blocking factors we're at. So that's what we mean when we say there's no relationship. We're specifically speaking about the interaction relationship where the levels of the blocking factor change how the independent variable and dependent variable relate. We're assuming that that doesn't happen, that the relationship between the independent variable and the dependent variable is constant no matter what level of the blocking factor we're at. Now, an interesting conversation that in my experience isn't often talked about, but I find it kind of fascinating, is this conversation about replication in the Latin square. So replication in the Latin squares asks, given that we have a Latin square, how can we incorporate repetitions in this Latin square design? So a Latin square just means we have a certain number of blocking factors. That doesn't necessarily mean that we can't replicate within that. So one of the big limitations actually of the Latin squares design is how sparse it is in terms of degrees of freedom. So in the 3x3 Latin squares, we only have 2 degrees of freedom for the error. In the 4x4, we've only got 6 degrees of freedom. This is problematic, and this gives a limitation to how much information we have going towards that error term. Now, we don't want the error term to be inflated, so don't get confused here, but we do want the error term to be accurate. We do want information about the error term so that we can be as accurate as possible. So replication is going to help here because it's going to add to these degrees of freedom for the error. It's going to give us this better estimate within the error term. Now let's see. So when we are using these small Latin squares, again, it's desirable to replicate because of this degrees of freedom issue. Now there's a few different ways that we can do this replication. Each of these is going to affect the results differently. You are welcome to check this out. So we can go through these 3 cases. They're presented in our textbook too. I can't quite remember where they're presented. We might have that in a slide coming up. So there's several ways to replicate these Latin squares. First is if we use the same rows and the same columns and we just added experimental units into that case. So we're using these same blocking factors and adding randomly assigned experimental units within those same blocking factors. That's one way in which we could replicate. We could also use the same rows but use different columns, and we can connect that back to our example using the same batch but different operators, or we could do vice versa, right? We could use the same columns or different rows. So case 2 is that we fix one of them and we let the other one vary. In case 3, we're letting both of them vary. We're using different rows and columns at the same time. So each of these are going to affect the results differently, and both the sums of squares and the degrees of freedom are going to be changing depending on what's selected. Now these equations are not particularly easy to write down. In fact, I think I've just, here it is. Okay, so table 4.14 and 4.16 in the textbook on page 158. This is where you're going to want to go to get that. I did that instead of writing these down. Because the degrees of freedom are going to be pretty easy to track. You'll get to see the differences in the degrees of freedom, but the changes in the sums of squares are a little bit more complicated. So I look at the degrees of freedom when I'm looking at why we're adding a replication, because again, the reason for adding this replication has to do with the total number of degrees of freedom in the model. So that's going to be a great way where you can go in, you can find the core of what that change is representing. But if you're interested in this, check out those tables 4.14 through 4.16. I think actually these three cases are indicative of those three tables in the textbook. So they should match exactly. You should be able to go in and check those out and see how each of these three cases, and depending on where we choose to replicate and how we choose to replicate, that can be incorporated. Now note, when we're making this design decision, how we can replicate, sometimes we get to make the call, but sometimes, as we talked about at the very beginning of chapter 4, the call is made for us by the specific design of the Latin square. So, the specific design of the experiment. So sometimes we're walking into a situation where we really can't change around the rows of the columns. We really have to replicate in a way that's going to leave one or the other of those fixed. So in that particular case, we're going to be using one of these by necessity, not necessarily by choice. In general, this is, of course, why we use blocking factors. We talked about this in the beginning with blocking factors, is oftentimes the situation puts us in such a case where we are forced to use blocking factors in this way. It's the same thing with replication. I'll say this is not as common. I haven't really seen it. I'm not saying it's not common in certain places. It's just something that I haven't particularly seen. So feel free to check out the textbook if you'd like more information on replicating within the Latin squares design. Now to close, we're going to have a very, very quick discussion of crossover designs. There's a lot here, and there's a lot more that we could go into outside of this now. But when time is a factor, we tend to slightly change the methodology that we approach our design of experiments with, and we lean away from these traditional designs into something that we call a crossover design, which accounts for these multiple different time periods. So in this particular case, it's going to be important to track what our letters are meaning. So we're going to have P time periods. We're going to be testing P treatment levels, and we're going to have N experimental units. Note that because we're going to have N experimental units, and we are grouping in groups of size P, incidentally, so the number of treatment levels, we're going to have N times P total experimental units. Now, when we have this particular setup, each group is going to be analyzed as its own separate Latin squares design. And we'll have a picture of this in a sec to try to help you make some sense out of this. And in fact, I think this is a very similar example to what's done in the textbook. This might be the exact example that's done in the textbook now that I think about it. Yes, it is. It's page 159 in the textbook, the dehydration example. So we're looking at the effect of two types of fluids on dehydration. All right. So we've got two different treatments. We've got, let's say, Gatorade and Powerade, two types of fluids on dehydration in 20 subjects. Now remember, we have two fluids, so P equals 2, and we said we're going to take each of these N subjects and we're going to group them into groups of P. So because we have two treatment levels, we're going to group the subjects into pairs. So in these pairs that we have the subjects group in the first time period, so again, remember we also have two time periods, P time periods, so two time periods. In the first time period, we're going to randomly select one subject from each pair and give them fluid A. So let's say Gatorade. And then the other subject is going to be given fluid B. That's Powerade. So time 1, we randomly select one subject to get one of the treatments, randomly select the other to get the other. Now note that in general, we're going to randomly assign the subjects to whatever the treatment levels are. So in this case, we have 2 time periods and 2 treatment levels, but we might have more in general. So we might have 3 treatment levels, and we're randomly assigning subjects grouped in threes, 1 to each of the 3 treatment levels for the first time period. So be careful with this. This works for 2, but think about how this extends for 3, say in preparation for a final exam question. Now, so that's the first time period. And then, of course, I hope you can see what's going to happen next. If we've got one subject from each pair given the first fluid and the other given the second fluid, what we're going to do in the second time period is switch. Now, in pairs, it's just switching. Again, in say when we have groups of 3 or 4 or 5, we're going to have 3 or 4 or 5 time periods, and we're going to have to kind of randomly order, making sure nobody got the same one. So this is where our little mini Latin squares designs come from. But in the second time period, we're going to switch, and the response is going to be, so at the end of the time period. But in the second time period, we're going to be switching the 2 fluids so that the first subject now gets fluid B, and the second subject gets fluid A. So what happens in between here is at the end of the first time period, we're going to respond, take the response, and then we're going to allow a period of time to pass. So thinking about this, we want to make sure that fluid A has kind of gotten out of person 1's system before we give them fluid B. Actually, this is a really complicated type of situation that we don't really talk much about. Actually, we're not going to talk at all about in this class, but this idea of compound effects and some other things that can go into this. So if you're interested in that, I think the book might touch on it. Honestly, I can't remember how much the book goes into this, but it's something to check out, and you can Google how we deal with this kind of situation, because it is really, really interesting. What if fluid A has a delayed impact? What if, hey, Gatorade takes 4 hours to kick in, but Powerade kicks in immediately? It's going to look like Powerade's awesome, but if we waited 4 hours before switching, the Gatorade effect is going to kick in, and it's going to look like it's a Powerade effect. So the amount of time that it takes to incubate or to have the treatment effect take hold is something very important. In fact, this is something I deal with pretty often professionally. I was just designing a study with a client where we were looking at asking this exact question: how long did the client think it would take for the effect to begin to show before we switched treatments? And what we don't want to do is to give a very, very important, very, very useful treatment that takes a little while to kick in, and we only give it for a short amount of time and then switch treatments. And then that treatment kicks in, but because we've switched treatments, we think it's the second treatment that kicked in, not the first one. That would be absolutely terrible to the effect of the study. It would make it look like the second treatment is way more effective than the first one, when in fact it's the first treatment that's very effective. So one way to do this is to just talk to a content expert about, hey, how long should we allow to pass before doing the next treatment? That is, how long does it take the fluids to flush out of the system? And then, of course, we tell them to take the different fluid. Now, because this is chosen randomly, person 1 might get fluid A or fluid B first. So you're just switching. You're just switching it back. Again, if you have more than just a pair of observations, you're going to be doing this for all 3 time points. If you have 3 treatment levels, you're going to be doing this for 4 time points. If you have 4 treatment levels, and you're just going to be randomly switching so that each subject only gets 1 and every subject gets 1 treatment level. So kind of the common sense, even though it might be a little harder to implement maybe than it seems in common sense. So for a picture of what this looks like, think about we've got the first pair, the second pair, the third pair, the fourth pair, the fifth pair, and we've got the different times, time 1 and time 2. And so in this first pair, person 1 takes liquid A or fluid A at the first time point, and that leaves person 2 with fluid B, and then they switch. Now note that this is randomly assigned, so I'm just randomly picking this first letter, and that actually determines the rest of the cell. So I randomly pick B, and then for person 1 in the second pairing, so person 2 has to get A, and then at the second time, person 1 has to get A, and person 2 has to get B. For the third pairing, person 1 was randomly selected B again. So you're going to get some replication here again because these are randomly chosen. These are randomly chosen. So in this, the design is actually looking at 10 Latin squares. Each of these is a little mini Latin square design, and that's how we end up analyzing this particular data. So again, each of these columns in each of the 10 pairs corresponds to the subjects, while each of the times corresponds to the, well, of course, the times, and each of the letters, again, this is Latin squares, we've got subjects, we've got time, each of the letters corresponds with the treatment. This ends our conversation on Latin squares. How do we analyze with Latin squares? How do we replicate with Latin squares? And then this kind of interesting extension when we have multiple time periods into the design that we're looking at here. So this one of the reasons that we go into this design specifically is because of the difference between replication and repetition. So remember, when we have repeated measures is multiple time points where we're observing the same participant. Remember, when we have replication is a different experimental unit under the same conditions. So in this case, because we're having the same experimental units or the same people at multiple time points with multiple fluids, this is going to be that example of replication, and that's why we need this new style of design, repetition, repeated measures. That's why we need this new style of design instead of the replication. In the next video, we'll discuss how to analyze Latin squares designs using the software R.